So I think we can start. Hello, everyone. I'm Alex, and I'm here to share with you some of the lessons that we have learned, the easy or the hard way, as we try to scale our online player account management platform, or PAM for short, in our attempts to keep up with the ever-expanding business needs. Quick backstory, OPAP is a company founded over 65 years ago, and although heavily reliant on technology and software, especially since the 80s, it wasn't until 2017 where we took the strategic decision to start implementing stuff in-house. So today we're proud to develop internally all the touch points that we have with our user base, be it retail or online, as well as core systems that are part of the gaming journey in both worlds, retail and online. We'll focus on PAM today, a pretty common component in the online gaming world. A PAM system is responsible for a user's registration, onboarding, upon which successful completion, they're given access to an online wallet where they can deposit and withdraw money from, hopefully place some bets, and then there's some heavy integration, every day more so with data analytics tools and CRM, whose output is usually some sort of loyalty-related campaign and bonusing. And all this is done under the prism of responsible gaming by offering the user tools like self-exclusion or limits to play responsibly. We'll focus a bit on this. So back in 2020, the deposit limits a user could set to themselves were deposit limits, essentially the maximum amount they allow themselves to deposit on their online account, buy limits, how much they allow themselves to bet, and loss limits, how much they allow themselves to lose, so it's bets minus the winnings. They could define those within periods of a day, a week, or a month. And given at the time that those all monetary related, we had decided to implement the limit management and checking functionality within one of PAM's busiest services, both in traffic as in development, which was the wallet service. The implementation was pretty rudimentary, so whenever, for example, for the buy limits, whenever a user placed a bet, we would fetch the user's limits, all the transactions from the database, calculate where they were, depending to those limits, and leave them or not, allow them or not to place a bet. Of course, it was optional in early 2020 to set those limits, and also our online offering at the time was limited to some lottery games and sportsbook, where maximum these kind of games generate tens, hundreds, maybe a couple of thousands of bets per month, which was the largest period. But this was about to change. So we're mid-2020, lockdown period, and OPAP fast forwards and launches our casino website. Now, casino games compared to sportsbook are a whole different beast. They started generating like 100 times the transactions compared to our previous games. So this had the side effects that there was a subset of our users who, especially towards the end of the month, would start to experience latencies. As important as the problem that was, it wasn't as urgent because limit setting was optional, so there was a small fraction of our users that were affected, but this would change as well. When we were notified that there was a new regulation that was about to take place a year later that had two big changes. One was the definition of the time limits, essentially how much a user allows themselves to spend playing, and also the regulation made all those limits we were struggling with mandatory, so all our user base should have their limits set. So we were in a bit of a pickle. If we were to see a high-level graph how that went, a bet placement would be sent to our wagering service, which would then ask Wallet to execute the transaction, and this is where Wallet would start doing stuff. Now it would retrieve the limits, retrieve all the transactions, check whether it's okay or not, and then the bet would be placed or not. And this is where we decided that, okay, it's definitely time to start refactoring this part because it wouldn't scale. And we started thinking aloud, was this maybe the right time to carve a new service out of our existing implementation? So in the maybe a bit dry, but definitely invaluable handbook on software architecture, Neil Ford and company define what they call granularity disintegrators, which, yeah, it's just a fancy way of saying reasons to split your service up. And they have defined 6 drivers that are used to guide and justify a decision whether to split a service or not. So we examined our use case against what they said. First, the first driver is scope and function. Was our service doing too much? Yeah, most likely. Second is code volatility. Do we have many changes in our code? Now, the particular thing here is that, as I said, Wallet is one of the most heavily developed services. However, the part of the limit checking mainly changes with regulation. So there's obviously a joke to be made here, but regulation doesn't change that often. So we could avoid errors in our limit functionality by carving out this part. Same more or less goes for the third driver, scalability and throughput. A user will normally only edit their limits twice, maybe 3 times in a quarter, but they interact with their wallet constantly. So we were 3 on 3 here. Fourth and fifth reason didn't apply that much to us. So fault tolerance is about having a part that fails too often split away so it doesn't take you down with it. It wasn't our case here. And security, more or less, we had the same requirements in our case. But there was definitely a case to be made about extensibility with the time limits requirement coming. We could refactor our stuff so that we could extend it as soon as we were required to apply time limits as well. So a new service was created. We refactored the ugly part as well with this opportunity. We were feeling very inspired, so the new service that would check limits was named Limit Service. And I'm tempted to say, yeah, that was it. But as most of you have already noticed, what we gained in scalability in terms of the transactions we could handle, we paid with 2 extra network hops. So we definitely added latency to all our users' bet placement. And we at least jeopardized the overall application's stability. So it beat us. It took us about 18 months to bite us, but a Tuesday, last February, it was when we rolled a new feature in our production, which enabled a new CRM campaign to run. And run it did. They sent a mass email to a huge chunk of our user base. Around 5 o'clock, 5:30, we were effectively down. And we couldn't get anything back up until at least 9 o'clock. Now, we did our postmortems to see what was going on and what we could do, and the outcome was that given our current infrastructure, our current architecture, our current code, and our current configuration, what that CRM campaign had done was to tip us over the maximum threshold of throughput that we could sustain. So we could add more hardware, re-architect, refactor, and reconfigure. So, of course, we tend to do everything, so we did all of what I just mentioned, but definitely where we got most value for our buck was configuration. So I will focus on the timeout configuration that we improved. Now, in a microservice architecture, and when you're using a blocking language like Java, whenever you make a synchronous REST API call, you wait. Now, the request that you're making to, its response time will fluctuate. It might fluctuate because of of a quirkiness in our implementation, like we saw before with our wagering service. It could be for a query that is too slow, or my favorite fall guy, the network, but it will fluctuate. The thing is that while you wait for someone to get back to you, there's two things that you need to keep in mind. There's someone that is waiting on you, but there's also the resources that you're blocking from serving other traffic. So there's a distinct, clear relationship between your maximum timeout configurations and the throughput that you're able to sustain. Now, there's a lot of timeouts that you can set, right? But there's two that we would like to focus today. It's the connect timeout, which is essentially how much you allow yourself to wait until a TCP connection is established with the party on the other side. And this generally, it's ought to be set. It's even more important when we're talking about network hops over the internet, even to a larger value that you would expect internally. Given that you have established that connection, then you need to decide, okay, how much am I going to wait for that response to come back? And this is where the read timeout kicks in. The key metric that we use as a benchmark here is take its request and measure its 99.9th response time percentile and use that as your benchmark. Now, depending on how much fault tolerant you wish to be, you will play within that threshold. In our case, we were lucky because the timeout configuration we had when we crashed was already too high. So we had the luxury to lower it, but not to reach those levels so that our error rate would increase. Now, of course, once you time out, the other party is not aware of that. So it will proceed to do whatever you ask them to do. And this is a whole new can of worms that was open. I'll just give you a sort of how we handle those cases. So when we implement operations that have side effects, then we try either by design or some other sort of mechanism, make them idempotent so that we can retry safely. Closing, there's no big gotcha that I wanted to share with you, but there's definitely no silver bullet and no clear answer to anything. Everything is context specific, but something can be as sexy as carving out a new microservice was in 2020, or as boring as just figuring out timeouts. The thing that we consider most important is the value that we give to business. By having this as your North Pole, then everything else will come. This is it. Thank you very much. I hope you enjoy the conference.